Right. Hope you can see the screen. Yeah, can you hear me well? Hello? Can you hear?
Yes, sir.
Okay. Okay, I think we we came up to prevalent mantle composition last time when introducing the mantle reservoirs. Here you can see the depleted mantle component and the bulk silicate earth, EM1 and EM2. So here we considered about these reservoirs, considering their amounts of depletion or enrichment, okay, with respect to neodymium and strontium isotopic compositions, right? Starting from bulk silicate earth, which is equal to the chondritic composition, okay? The chondrite composition is similar to this one. So this composition has been derived from the chondrite composition. And here in this region, you have in this region, okay, you have modes, mid-ocean ridge basalts compositions, right? And in this region, what you have is mainly oceanic island basalts composition. And we have DM, depleted mantle, and this depleted mantle produces this mob, mid-ocean ridge basalts. And the deeper melting produces these ocean island basalts, right? Like core-mantle boundary in that region melting, which does not frequently taking place like in the mob region, but they produce a little bit enriched composition. So enriched composition means high strontium composition, but low neodymium composition. So enrichment in this diagram should go this way. Okay. So the depleted mantle is low in in strontium isotopes, but it's high in relatively high in neodymium isotope composition. So when it goes to the enriched mantle region, that means in this region, in the high strontium region, where you can easily find enriched compositions. So enriched compositions means high strontium values and low neodymium values. Okay. Right. And the depleted mantle is that, and the EM and EM is divided into two, EM1 and EM2, as I mentioned. So EM1 is here, it is low strontium, relatively low strontium compared to the EM2, right? EM2 is having very high strontium ratios, which is actually even greater than 0.720, right? That means you can imagine how enriched that is, right? This is still 0.706, right? So 7.2 means it's farther away, right? And EM, you are having like 0.705 average like composition. So in comparison to the EM2, EM1 is not that enriched in terms of strontium isotopic compositions, right? Neodymium does not have big variation, but neodymium ranges around this value, right? I mean less than that value, less than this value. That means here, right? Less than that value. That means at least go down this way, and EM2 goes like that, right? So the trend of EM is like this, right? Trend of EM is like this. And we have another component, as I mentioned in the previous cases, in the last week, that you have some special component called high mu, right? This high mu is defined in terms of lead isotopes, right? We are going to consider lead isotopes today, and high mu is derived by lead isotopic compositions. But still, in the neodymium and strontium isotopic composition, also you can see some sort of deviation from the normal Mantle array. So, what is the Mantle array? Mantle array means the normal average Mantle composition. I mean, all Mantle samples starting from DM to EM enrichment, right? So, this is what we call the Mantle array. Okay, so this is the Mantle array, but this high mu is deviating from that Mantle array, right? So you can see it's deviating. So this SH means St. Helena. It's a location, right? It's an island. There you have this mob, Indo-Rich basalt type, but that basalt type is different from normal mob. So therefore, and also they identified using lead isotopes, right? So this St. Helena samples represent high mu composition. So sometimes it's termed as St. Helena component. Okay, without saying high mu, some people term it as St. Helena component, like, right? So anyway, it's a little bit deviating. So that indicates there is a separate reservoir should have been there in existing in the mantle, right? So although the prevalent mantle composition lies in between DM and EM, or average EM values or OIB values, it's also kind of a restricted section of the mantle. So therefore, people take this also as a reservoir in some cases, right? Otherwise, they just take as the prevalent mantle. Prevalent mantle, that means the normal average existing mantle composition, like, because it is in the middle, right? It's in the middle, so it's something like average of all this mantle array. So that's why people have termed it as prevalent mantle. But uh, considering the number of or the amount of sample recovered from oceanic basalts, there is idea that there should have been a separate reservoir also called Prema, right? So it's that, and which is frequently, I mean, it's not rare also, but the composition is very restricted, right? It's not changing much, right? It's concentrated around this area. But unlike other mobs, you can see very wide variation, right? But this one is very restricted. Okay. And one more thing you can identify using this diagram. The same diagram is there. You have DM here, depleted mantle, right? And you have high mu, we can ignore for the time being because it's a small variation, and also the prima we can ignore, right? Other major reservoirs we'll just take into account. DM, EM1 is there, and EM2. Actually, EM2 is somewhere some away from this place, right? It's moving that way because its a strontium isotopic composition is very high. Okay. So anyway, if you consider these three components, right? Just these three components, DM, EM, and DM, EM, and EM1 and EM2, right? You can consider them, and you will see if you draw some line connecting those reservoirs. Okay, if you draw some lines connecting these three reservoirs, what's resulting? It results a triangle, right? Almost, it results a triangle, right? So this indicates a very important inference from this composition, isotopic composition. Actually, this is consistent with lead isotopes also, because the other dominant isotope type we have to consider is lead isotope. So we will go to that today. But before that, you can just think that this DM and EM, right, can produce together with EM2, right? EM1 and EM2, including DM, right? Can produce all this compositional range. If you mix all these three reservoirs, this one, DM, and this one, and EM2, right? If you mix these together, right, you must get some value in between, right? That's normal idea. For example, if you have two reservoirs, right? So you have one reservoir here and another reservoir, another reservoir here. And if you mix these two reservoirs, what is resulting? This is, say, A, and this is B, right? If you mix A and B compositions, what should happen? Whatever the resulting composition you should get should be lying along this line, right? Along this line. That means somewhere here, here, or here, right? Depending on the amount of A and B contributions, right? For example, if you make 50% of B and 50% of A, you ideally you must result with a composition like average composition here, right? So that means it's a mix. We call this A and B as mixing end members, right? So geochemically also this theory applies, where we consider them as the mixing end members, geochemical end members, right? So this A and B can produce resulting compositions in between these two. So here the mixing or the resulting composition varies along this line, right? This is a straight line, right? If you draw it properly, it will be a straight line. So depending on the contribution, whether you get it here or whether you get it here is determined. It's something like the solid solution, right, in minerals. Right, so therefore, this is a linear type of mixing. So therefore, we call this is binary mixing. Okay, this binary mixing can happen, for example, DM and EM, right? So in this region, if you have samples, you can explain their chemistry by using this type of binary mixing, right? For example, here, DM and this component somewhere here, right? If you have some basalt here composition as end member and another basalt here end member, if you mix those two basalts, because they are melt, so you can mix together, right? So you can mix together and form a composition somewhere like here, somewhere lying here. So this happens naturally also. This happens naturally also because magma mixing is taking place frequently in the mantle, right? Magma mixing, because these magmas are generated drop by drop. Okay, partial melting. We call it partial melting, right? It's not the complete melting of a whole mantle mass. It's partial melting, and drop by drop this melt is accumulated, and once it accumulated to a significant volume, it starts to migrate upward because of density difference. The rock overlying there, the surrounding rock or the ambient rock is highly dense, right, compared to the melt. So therefore, melt can easily migrate upward. This migration is taking place mainly along the grain boundaries of minerals, and also along the weak zones like faults, fractures, like weak zones, right? So this drop by drop migration accumulates material, and then it goes up as a conduit, right, as a conduit of magma flow. So while going upward like this, several conduits of magmas can mix together in upper levels, because in the upper levels the pressure is low compared to the deeper melting region. So therefore decompression is taking place. So it's almost like the magma, the conduit becomes more released, like more more relaxed like, right? So therefore there is possibility for spreading through along the available fractures also. So then several types of magmas can mix. So such magmas can also produce like this composition. Actually, that's the reason why these oceanic basalts are having such a vast range of composition, right? Otherwise they will be restricted to somewhere here or here, like that, but it's not like that. So you see, this is from a single ocean. For example, this blue color is from one ocean, from Atlantic Ocean. Okay, this yellow color is from Indian Ocean. So you have a vast composition, wide range of composition, right? It's because one reason is it's due to magma mixing. The other reason is different compositions prevailing in different source regions, right? That is, the both things are there. So anyway, this mixing phenomena is applied there for this partially molten magmas, right? So that's why I mentioned at the very beginning that we are using these isotope ratios not to determine any age. So we are not going to determine any age correlations, but we are trying to identify geochemical processes, right? So once we know the compositions, then we can model these compositions backward, so that whether to understand whether it is a mixing product or a pure just a melt product or something like that, right? So this is this is the normal situation. uh, I had a short power cut. Do you hear me? Do you hear me?